All right, so in this video, we're going to start by talking about the natural log. And when we say natural log, we're talking about the ln of x, which we know is the generic log, but with a base e. So we don't necessarily write the base e, we rewrite it as a natural log, so ln of x. And the derivative of that natural log of x would be 1 over x. Now the chain rule would apply here. You'll see that in the example we work here in just a minute, but I don't want you to think of that as two separate formulas. So we've got our derivative now of the natural log function, and from there we can expand as necessary. Now we are going to prove this one. So the proof, we're going to start by letting y equal the natural log of x. Okay, I'm going to take that now and I'm going to go back into exponential form. So in exponential form, that would be e raised to the y equals x. And then I will go ahead and dx both sides. When I dx both sides, the derivative of the left would be the e to the y, but since we're taking the derivative with respect to x, this is also going to have to be a chain rule now as we take the derivative of y with respect to x. And on the right, that's going to equal 1. And then to solve for dy dx, we would get a 1 over e to the y. And our y, we know, is the natural log of x. So dy dx equals 1 over e raised to the natural log of x, which, of course, from the earlier video, we know is just going to be the x in our denominator. All right, so a nice simple proof as to why that is what it is. But even more importantly, it allows me now to circle back and show you why the derivative with respect to x of e to the x is e to the x. Okay, so to prove this one, we're going to let y equal e to the x, and now we're going to convert this into its logarithmic form, which would be the natural log of y equals x. And then we're essentially going to do the same thing we did a moment ago. I'm going to ddx both sides, and when I do that, the derivative of the left, okay, so the derivative of a natural log, that's going to be 1 over the inside. So in this case, it would be a 1 over y, and then back times the derivative of the inside. So the derivative of y with respect to x would be that dy dx. And on the right, we have our 1 again. So as I solve this for dy dx, I multiply the y over, and we know from the start that that y was equal to e to the x. Therefore, our derivative is e to the x. So two really important results here. One you saw a moment ago, but now we were able to prove it. And the other, of course, is a completely new derivative now that we're able to do in Calc 2. All right, so now we're ready to take a look at an example here. We've got function g of t that looks like it's going to be not only a product rule, but it's got some chain rules involved as well. So when I look at this, I see this as my first and this as my second, and we know that the derivative of a product rule would be, or using a product rule would be the derivative of the first times the second plus derivative of the second back times the first. So our g prime of t. So derivative of that first would be the 1/2 t to the negative 1/2. Okay, so there's the derivative of this guy is that, times the second, which would be our cosine squared of natural log of t cubed, and then plus derivative of the second back times the first. I'm going to go ahead and copy down that square root of t so I don't forget about it. And so now I can completely focus on the derivative of that second. So for the derivative of the second, we would have to start here with this chain rule with this 2. So the 2 is going to come down, keep the inside the same, subtract 1. So that's going to be our 2 cosine to the first now of natural log of t cubed. Then times the derivative of the inside. The derivative of the inside would be that cosine to start. Derivative of cosine is going to be a negative sign. Keep the inside the same. And then back times the derivative of its inside. I'm going to move down here for that. I'm running out of screen space. So the derivative now of this would be 1 over t cubed. and then times the derivative of its inside, which would be 3t squared. All right, so let me go ahead and label this real quick so everybody can see it a little bit better. That's the derivative of the first times the second. This whole thing right here is the derivative of the second back times the first. So if there are any questions, I'm almost certain it would come in from this guy. So let's kind of talk through this again. So if I'm taking the derivative of this, I multiply the 2 down, the inside stays the same, and we subtract 1. So the 2 comes down, inside stays the same, we subtract 1. Then the derivative of cosine would be our negative sign, keep the inside the same. Derivative of the inside of it would be this 1 over t cubed for that new natural log derivative we learned. And then the derivative of the inside of it would be the 3t squared. So again, this is an unsimplified derivative. My math lab would want you to probably simplify, clean it up a little bit. But for written work, whenever I say unsimplified derivative, stringing it out just like this will be what I'm looking for. Okay, so now we're gonna go a little bit deeper into some things, and I'm gonna talk about the case where the derivative of the natural log of the absolute value of x is still gonna be that 1 over x. Okay, let's talk about why. There's essentially 2 cases. Case 1, what we're going to investigate is when x is bigger 0. And the second case we're going to talk about is, of course, where x is less than 0. X can't be 0 because it's in a denominator, so we can talk about positive versus negative. Where the case where x is bigger than 0, that's trivial. That's been the case the whole time, right? Even if this x right here is positive, the absolute value bars don't mean anything. It's already positive. So this is the trivial case. But when it's less than 0, let's take a look at it. So when it's less than 0, and I want the derivative of it, to get rid of those absolute value bars, remember what's inside the parentheses for a log always has to be positive. So if x is negative, then I'm going to need a negative x right there. So follow me. If x is a negative 5, if I put a negative 5 right there times a negative, then it turns positive. So that's the only way we're allowed to, in fact, take the natural log of something is if this quantity is positive. So when I come through now and I take its derivative, I'll get my 1 over negative x times the derivative of the inside, which would be our negative 1, hence leaving us with this 1 over x. So no matter what, no matter if x is positive or negative, when we take that derivative of the natural log, we always get this 1 over x, okay? And that's going to now help us with our integral. So we know that the derivative statement is true. Therefore, the integral of 1 over x dx is going to be equal to the natural log of the absolute value of x plus c. So this was a much more powerful statement. And so when we take the derivative now and think of this as the antiderivative, it's now going to give us the ability to integrate this 1 over x. Just don't forget the absolute values have to be on the x value quantity, if you will, for that natural log when we integrate these. So let me go ahead and clear the screen. We'll take a look at an example that has been kind of overlooked for quite a while. All right, so we're going to take a look at the integral for tangent of x. If you had me for Calc 1, you probably heard me say it quite a bit. When you came to these trig integrals, it was interesting some of the things you knew and some of the things you didn't know, and it all came from the derivatives. We'd never really talked about the integral for tangent of x, yet somehow we knew what the integral for cosecant cotangent was, right? Kind of strange how some of the things we knew, some of the things we didn't. Well, a lot of times we were at the mercy of not having the Calc 2 tools available to us at that time. But now, since we have this new integral that we just talked about, we're able to figure this out. Now, since we can't directly integrate, of course, we're going to have to manipulate the function. And I'm going to go with sines over cosines, and then just use a basic u sub. If I let u equal cosine of x, my du would be a negative sine of x dx. Don't forget that dx on the end there. And therefore, negative 1 over u du would be my integral. And so now the 1 over u goes to the natural log of the absolute value of u, and then we'll throw back our cosine in there, and we're back into x's, and we have our final answer. So once again, we weren't able to do that in Calc 1 because we didn't understand the natural log component yet, but now that we have that available, it's going to open up a whole nother world to us as to what we can do. Now, for me, when you turn in written work for me, this is a perfectly acceptable answer. I do want to give you a little bit of a heads up though. Using our logarithmic properties that I'll address here in momentarily, this negative can come up here. And if I have cosine raised to the negative first, that's going to be 1 over cosine, which is going to be secant. So this is equivalent then to the natural log of the absolute value of secant of x plus c. I don't care which one you give me. The book will address probably this one. My math lab might address this one as well, but these are both the exact same thing. Again, just using your properties of logs to take this negative up. Cosine raised to the negative first is going to be 1 over cosine, which is secant. Okay?